This presentation on hydraulic pumps is the second in a series of 8, which provides a comprehensive introduction to hydraulics, the science of fluid under controlled pressure. I'm Paul Cook for Sperry Vickers. Pumps fall into two basic categories: positive displacement and non-positive. Non-positive pumps are used primarily for circulating or transferring fluids. Examples would be the water pump on an automobile engine, or one used in a dishwasher or washing machine. Let's look at a schematic. Most non-positive pumps operate by centrifugal force. Fluids entering the center of the pump housing are thrown to the outside by means of a rapidly driven impeller. There is no positive seal between the inlet and the outlet ports, so the pressure that's obtained is a function of the drive speed. The output flow decreases as the resistance increases. These features make it impractical to use non-positive displacement pumps in most present-day hydraulic systems. Positive displacement pumps, on the other hand, deliver a definite quantity of fluid for every stroke, revolution, or cycle. This illustration shows that on the intake stroke, fluid enters the pump through a check valve. On the forward stroke, the check valve closes, sealing off the inlet. Therefore, the fluid displaced as the piston is moved forward must flow through the pump outlet. The pressure is determined by the workload. This principle applies to all positive displacement pumps, whether they be vane, piston, or gear type. Perhaps the simplest and easiest to understand is a gear pump. One gear driven by the drive shaft meshes and rotates another, called the driven gear. Both are contained within a close-fitting housing. A partial vacuum is created at the inlet as the gear teeth unmesh, and fluid flows in to fill the void. Then the fluid is carried around the gears to the pump outlet. As the teeth go back into mesh, oil is forced out through the outlet port. As this operates, we now have high pressure at the outlet and less than atmospheric pressure at the inlet. This condition is referred to as unbalanced hydraulic loading. Gear pumps today are highly efficient units, capable of operating at pressures of up to 3,000 psi and speeds in excess of 2,000 RPM. This performance is at least partially the result of the addition of bronze-faced flexible wear plates. These plates are pressure-loaded against the side faces of the gears, reducing clearance to a minimum. Passages in the wear plates also permit oil, under pressure, to extend farther around each gear to reduce the unbalanced hydraulic loading inherent in this type of pump. Sperry Vickers gear pumps range in size from 7 to 50 gallons per minute at 1,200 RPM, although considerably higher drive speeds are permissible. They're available as both single and double units. Other manufacturers have gear pumps that are rated as high as 100 gallons per minute. Vane pumps seem to have been favored in the machine tool industry, perhaps because of their high efficiency, low noise level, and long life. In an unbalanced vane pump, a slotted rotor is splined to the drive shaft and revolves inside a cam ring. Vanes are fitted into the rotor slots and follow the inner surface of the ring as the rotor turns. A minimum starting speed of 600 RPM will throw the vanes out. Then, centrifugal force and pump outlet pressure under the vanes hold them against the ring. Pumping chambers are formed between the vanes and are enclosed by the rotor, the ring, and two side plates. With the ring offset from the center line of the rotor, the chambers increase in size and take in fluid as they pass the pump inlet port. Then, as they cross over center, the chambers become progressively smaller and fluid is expelled at the pump outlet. This pump has a somewhat limited pressure capability because of its unbalanced hydraulic loading. Its displacement, however, can be varied or even be reduced to zero by moving the ring towards the center line of the rotor. Now, a balanced vane pump operates in the same manner as an unbalanced unit, the difference being that the inner contour of the ring is an ellipse rather than a circle. This configuration forms two sets of pumping chambers. They're on opposite sides of the rotor, but are interconnected through passages within the housing. Forces caused by pressure buildup on one side are canceled out by equal but opposite forces on the other. The displacement of a balanced design vane pump cannot be adjusted. However, interchangeable rings with different cam contours or widths are available, making it possible to quickly modify a pump to increase or decrease its delivery. Another modification we sometimes require is to reverse the drive shaft direction. We would, however, have to ensure that the flow direction within the pump is not reversed. The key to this situation is in the repositioning of the ring, so that the major diameter of the inner cam is rotated 90 degrees from its original position. By doing this, the pumping chambers will continue to increase in size as they pass the inlet porting and decrease at the outlet. Flow through the pump will then remain the same, even though drive shaft rotation has been reversed. Now, let's focus on three different types of balanced vane pumps Sperry Vickers currently manufactures. All are similar in operation, but differ in construction and pressure capabilities. We'll first discuss the pump patterned after the original model, patented by the company's founder, Mr. Harry Vickers, in 1925. Called the V104 series round pump, it has a replaceable pumping cartridge, which consists of a ring, rotor, and vanes sandwiched between two bronze bushings, each containing two inlet and two outlet ports. Hubs on the rotor fit into supporting hubs in the bushings, which serve as bearings. The drive shaft only requires a small pilot bearing in the pump cover and a somewhat larger one at the front to accommodate any minimal side loading. A 2-diameter pin keys the cartridge assembly together and fits into one of two holes in the pump body, which are located 90 degrees apart. The hole that we select determines whether the pump is assembled for right or left-hand rotation. The pump cover serves as a clamp to hold the cartridge assembly together. Care must be exercised when tightening the cover bolts, as over-tightening may cause the pump to seize. Under-tightening will result in loss of efficiency. The V104 is an extremely quiet and efficient pump, but its pressure and drive speed limitations of 1,000 psi and 1,200 RPM limit its use in many of today's applications. So, where higher pressure and drive speeds are required, as in most mobile vehicle applications, the Sperry Vickers Model V20, or square pump, is more apt to be found. With permissible speeds up to 3,400 RPM and pressure capabilities of 2,500 psi, it's well suited to many vehicle applications. In this pump, the rotor and vanes are held against the machined surface of the body by a spring-loaded pressure plate. The outlet port is in the pump cover, enabling outlet pressure to assist the spring in holding the pressure plate firmly in position. The square cover permits the outlet port to be assembled in any of four positions with relation to the inlet, which is in the body. This, of course, simplifies piping during pump installation. By removing the cover, we can see the two pressure passages through the pressure plate, as well as the small holes which direct oil at outlet pressure to the underside of the vanes. With the pressure plate removed, we can see that the slots in the rotor are radial, and while it may be more difficult to see, the vane tips have a symmetrical radius. This means that neither are affected by drive shaft rotation. Pump rotation is established by the position of the cam ring, removing the ring from the locating pins and replacing it with the opposite side facing the pump body automatically rotates the cam 90 degrees, and the pump may be driven in the opposite direction. Arrows on the ring indicate proper rotation. The varying sized holes in the ring are called overpass holes. They improve pump inlet conditions by permitting oil to flow into the cartridge from both the body and the pressure plate side. Reassembling the pump is equally simple. With pressure plate loading being a function of system pressure, it's only necessary to tighten the cover bolts to their specified torque. But don't forget the little spring and O-ring seals. Now we come to the third and final version, the Intravane series. This one is a truly high-performance unit with deliveries of 109 GPM and pressure to 2,500 PSI, 3,000 PSI in smaller units. It, too, is a cartridge-type pump, where the ring, rotor, and vanes are contained between a pressure and wear plate, held together by two small screws. These cartridges, incidentally, are available as pre-tested replacement units to speed pump overhaul and reduce downtime in the field. They're usually assembled for right hand, but can be reversed by reversing the ring, rotor, and vanes. The cartridge is accessible after removing the back cover, which in this case contains the pump inlet port. It may be necessary to grasp the cartridge firmly and give it a slight twist as you pull it out of the body. An O-ring seal and backup ring around the hub of the pressure plate prevent leakage into the shaft seal area, but also resist removal of the cartridge. Now then, you'll note something different when we examine the cartridge. The two previous pumps had solid vanes, and outlet pressure acted under their entire bottom surface to hold them firmly against the ring. In these pumps, with their large vanes and high pressures, the forces involved could reduce both ring and vane life due to high vane tip loading. Remember, force equals pressure times area. As a remedy, holes were drilled through each rotor segment, extending from its outer surface to the bottom of the vane slot ahead of it. By chamfering the tip of each vane, the pressure at the chamber behind it acted on both its top and bottom surface, keeping it in hydraulic balance. One further step was necessary to be sure that the vanes would follow the contour of the ring at high drive speeds. Now, this was accomplished by incorporating an intravane, or a small insert in each vane, and permitting outlet pressure to act in the small area between them. This pressure, plus centrifugal force, holds the vanes against the ring to assure proper tracking at any permissible speed. The intravane is used successfully in high-pressure machinery and in press circuits as well as mobile vehicles. To make it more compatible with the temperature extremes in which mobile units must operate, bronze-faced steel flex plates have been added to the cartridge assembly. They're much like and serve the same purpose as those mentioned previously in our discussion on gear pumps. Although interchangeable with the original intravane cartridge, they're not required and unlikely to be used for machine tool application at the present time. Piston pumps, because of their high efficiency, high pressure, and high price, were used in aircraft and military applications, as well as in large hydraulic presses, where their cost could be justified. Today, however, simplified designs have lowered their costs, while still retaining the beneficial features of piston-type units. As a result, they're being used in increasing numbers in both mobile and industrial applications. All piston pumps operate on the principle that a piston reciprocating in a bore will take in fluid as it's retracted and expel it on the forward stroke. Two basic designs are available, one known as a radial and the other an axial piston pump. A radial pump has pistons which reciprocate radially in a cylinder block, which rotates on a stationary pendule, and inside a circular reaction ring. Some force, usually charging pressure and/or springs, holds the pistons out against the inner contour of the ring. With the ring offset from the center line of the cylinder block, the pistons reciprocate in their bores, taking in and expelling fluid through porting in the pintle. Moving the reaction ring will change the length of piston travel, thereby varying the pump displacement and output flow. In axial pumps, the pistons are parallel to each other and to the cylinder block axis. They may be either bent axis or inline units. The cylinder block in a bent axis pump rotates at an angle to the drive shaft. The pistons are fastened to the drive shaft flange by ball joints and are forced in and out of their bores as the distance between the cylinder block and drive shaft flange changes. Pumps of this type may be fixed or variable displacement. The latter, with proper controls, will even reverse the direction of flow if the yoke is moved across center. The cylinder block of an inline pump fits over and is driven by splines on the drive shaft. The pistons fit into bores in the cylinder block and attached to shoes. The shoes, in turn, are held against an angled swash plate by a spring-loaded retractor ring. As the shaft and cylinder block are rotated, the pistons reciprocate in their bores as they follow the angle of the swash plate. In fixed displacement units, the swash plate angle is determined by a machined surface in the pump body and cannot be changed. Variable models have a movable yoke, which holds the swash plate and permits it to be pivoted to any desired angle up to the maximum displacement of the pump. Here, too, various controls are available, from manually controlled levers to pressure compensators. A compensator is a device which permits full pump delivery up to a preset maximum pressure. When this setting has been reached, a small spool valve shifts and directs fluid into a piston, which destrokes the pump, reducing its output to only what is required to maintain pressure. When outlet pressure drops due to changes in the workload, a spring returns the yoke to its full stroke position. By reducing pump flow, instead of dumping it over a relief valve, heat losses are held to a minimum, with a commensurate saving in energy. Okay, that wraps up our discussion of hydraulic pumps. As I'm sure you've come to realize, the pump is the heart of the hydraulic system, just as your heart serves as a pump for your circulatory system. It isn't a bad analogy at all. An ineffective pumping mechanism means almost as much trouble for a machine tool as it does the human body. I'm Paul Cook for Sperry Vickers.